Hi everyone, and welcome to a quick introductory video and tutorial for the EPC Online Thermal Calculator, which is part of our GaN PowerBench set of tools. My name is Asad Hello, and I'm a thermal mechanical engineer with EPC. Thank you for your interest, and I hope this video will help you navigate and benefit from our online thermal application. Before we go over to the online calculator, I would like to talk a bit about the background of the online thermal app. So as you may know, the GaN devices have been gaining popularity over silicon MOSFETs as more powerful and more efficient alternatives. And that's due to a set of factors. GaN devices demonstrate exceptional performance since they are smaller, they switch faster, and have a lower on resistance, and thus are more efficient than their silicon counterparts. Moreover, GaN, having a higher band gap, is also more capable of high voltage switching and is thus a better candidate for high power applications. But even with their higher efficiency and lower losses, all electronic devices lose some power as heat. So to unlock the full capabilities of gallium nitride in high power applications, a simple thermal management solution may be required as part of the design, such as the heatsink, similar to the one shown in this figure. So thermal management and design may cause some electronic designers to remain hesitant and cautious in transitioning from silicon to GaN, and mainly due to some misconceptions relating to the device scale and the complexity of the thermal design. EPC devices benefit from a smaller device size, both electrically and by saving board space, but that does not have to come at the expense of thermals. EPC devices, either chip-scale packaged discrete devices or QFN packaged power ICs, have an exposed die, which gives them a lower thermal resistance from junction to case when compared to other packaged MOSFETs and other packaged devices. This allows to benefit from a simple cooling solution and minimizes the thermal resistance in the path of backside cooling. So CSP devices can be cooled adequately, but the thermal overall performance depends on many parameters relating to the thermal solution, such as the thermal interface material and the heatsink used. So to analyze this thermal system, one should consider all of these factors together, either using full simulations or some sort of reduced or approximate models, with some benefits and drawbacks to each. While full numerical simulations provide the most accurate and comprehensive analysis, they are numerically expensive, and commercial licenses of simulation softwares are expensive as well, and running these simulations requires a lot of time and user experience. On the other hand, simple solution also requires a simple analysis as well. So to simplify the thermal analysis, the online thermal calculator we present was developed based on reduced thermal models, which are more desired, especially at the early stages of design, and for a few reasons. So first of all, reduced models can get quicker analysis results in minutes rather than hours. They have an acceptable accuracy and also require minimal user experience. So for the following reasons, EPC, in an effort to provide thermal design support, has added an online thermal calculator to the EPC website to help designers with device selection process, to assess the thermal feasibility of their designs, and if needed, also to assess these designs with different proposed thermal solutions. So without further ado, let's move to the EPC website and check out the online calculator. So you can find the app on EPC's website under design support and as part of the GaN PowerBench. And this is a collection of very useful apps and tools that EPC have added to support electronic designers. So here's the GaN FET calculator. Okay, so for a quick walkthrough through the user interface and the different panels, When you first access the app, you will find a short paragraph giving a brief description of the tool of the app, and there's also a user guide that you can use for reference. Next, you will see a schematic and a prompt to use the different panels in the app to set up the thermal system. The schematic shows a GaN device mounted on a PCB with a certain number of conductor layers. And it shows the thermal solution, in this case, a heatsink mounted, and there's a heat spreader, some TIM material as well. The different parameters of the cooling solution can be modified later, and the schematic will update accordingly. Also, the thermal resistances of different structures through which the heat will be conducting from the junction to ambient are also represented in a circuit diagram. And this is what is later solved for the overall temperature rise in the active devices. So next, we can start by defining the input parameters for the model. And this is done in a set of 3 expanding panels relating first to the device structure, and then the PCB construction, and third, the backside cooling solution. So let's begin with the first panel. The first panel pertains to the device. The calculator can analyze either a single device configuration, or it can also analyze 2 devices in close proximity, which represent the widely used half-bridge layout. And also this can be symmetric or asymmetric. And when you select one of these options, you will see that on the right-hand side columns, we have a drop-down menu from which we can select the different EPC devices. And when we select a device, you can then see the thermal resistance to the case and thermal resistance to the board. When we select 2 devices, another panel will also appear. In this case, because we have chosen the symmetric 2 devices, we only have one option to select the same device. If we select an asymmetric layout, we then have more options to select. And we can see the different parameters for that device. Next, the next thing we can also define is from these input panels over here, we can see that we can define the losses in each device. And these can be obtained from estimates from the electrical design. And we can set that the unit is in watts. And also based on the die area, we can also calculate the power density in each of these devices. So to improve also heat dissipation into the board, the different devices can have a certain number of vias in pad, and we can also define that number over here. And this will give us a certain number of vias per millimeter squared of die area. And you may have noticed that also we can define the ambient temperature, and this will be used for all the subsequent temperature calculations. And for the 2 devices, we can also define the spacing, which is separating these 2 devices. Another option is we can unselect the vias and choose not to have any vias in pad. But if you notice, vias improve the in-plane thermal conductivity into the PCB. So next, we start thinking about the cooling that is available for our PCB, and we can determine that using these 2 checkboxes. So the first one states that there is minimal airflow to the PCB, and then we can just choose not to model the heat dissipation from the PCB to ambient. And the next one determines if we have a case side cooling solution, which is either heatsink or a heat spreader, and we can choose to select that. One thing is that we cannot choose not to model any of those, because then there wouldn't be any heat dissipation, neither from the PCB nor from the case side, from the heatsink. So we here define that there's some airflow to the PCB, and let's also define that there's some case side cooling by using a heatsink. So the next panel is for the PCB cooling, and it would mainly depend on the PCB construction, which is defined in the PCB parameters panel. And we can first see that there's certain parameters that we can define, mainly the stack up of the PCB, the conductor area from which heat is dissipating into ambient, and the PCB thickness, as well as the airflow, which is flowing across the PCB. So the PCB stack up can be chosen from a different set of options. You can choose a different number of layers and a different thickness of copper for the conductor layers. And there's also a custom option where we can use sliders to determine these two parameters. So let's revert back to one of the chosen options. And there's a similar thing for the PCB conductor area. We can choose an estimate for the PCB size, or we can also use a custom user set parameter. And we can see it here in both units of millimeters squared and inches squared. The PCB thickness can also be chosen as a standard, and this considers a certain thickness of the interlayer insulator and the thickness of copper, and chooses the right thickness. Or we can set these parameters, set the PCB thickness, or set the dielectric interlayer thickness and the core thickness, and we'll get a certain PCB thickness. So we'll go with the standard for now. It should be good enough. And the last thing is we can also set the airflow that's flowing across the PCB. And these conclude the PCB parameters. And after setting the device and the PCB input parameters, we can then choose to add a heat spreader or a heatsink and define those parameters as well in the next panel that relates to the case side cooling. So with any heat sinking method, we would need a thermal interface material to improve the thermal conductance from the die to that sink surface. And these TIM properties are also defined in the first set of widgets. So here we can define the conductivity of the TIM pad. And the pad is that grayish TIM that goes on top of the die and is sandwiched between the heatsink and the FET. The highest conductivity that we use from our suppliers is around 17, but we can use a high conductivity of 10. And the gap is the distance from the die to the sink surface, where the TIM would be filling that gap. And we can set that to around 0.3 or 0.4, depending on the mechanical construction. Next, we can choose to add a liquid or a gel TIM material, and that helps to conduct heat also from the sides of the die. And this is more beneficial, especially for the smaller device sizes, where the areas of the side faces is comparable and sometimes even more than the area of the top face, and it can help with the heat conductance. And this liquid fill can cover the side faces of the die and improve heat conductance. We can also define that by defining the thermal conductivity. and also defining the amount of fill that is placed around the device. So there's a minimum and there's a maximum, and the calculator helps in making sure that there's some limitations to what's the minimum that the user can input. Next, we can decide to add a heat spreader before adding a heatsink, and this helps by spreading some of the heat in the lateral direction and increase the heat that is going into the heatsink. And a heat spreader can be added, and the parameters that are needed are the side dimensions of the heat spreader and the thickness of that heat spreader. And the size of the heat spreader determines the area of heat transfer into the heatsink. So next we get to the heatsink, and for that we can define the heatsink using different parameters. The performance can either be defined as a thermal resistance to ambient, or RSA, as shown here in units of degree C per watts. And this can be obtained from manufacturer data sheets, or the heatsink performance can be defined by using an overall heat transfer coefficient from the surface of the sink. And we can also define that in watts per unit area of the heatsink per degree C or degree Kelvin. So a third option, which is provided in this online calculator, is that we can use an embedded calculator to calculate the performance of our heatsink. So we notice that if we select this heatsink calculator option, we'll get a new panel entitled with the title heatsink calculator, and which prompts us to design our own heatsink. So with that, first thing we will see is the figure and the required parameters of the heatsink. And these required parameters are for the different geometry of the heatsink: the width, the length, the number of fins, and the fin height and thickness, and the base thickness. It also requires the material of the heatsink as well as the emissivity of this material. And there's some suggestions based on typical emissivity values for different surface finishes, like paint or anodization or polished aluminum. So also we can see that if we vary some of these parameters, we can see the updated heatsink profile and make sure that we're not designing something that's not feasible or that has some collisions or something like that. So whenever we're happy with the heatsink profile, we can go down and look at the calculator results. And also we can choose to change the airflow to that heatsink. So by increasing the airflow, we would be reducing the thermal resistance to ambient and improving conductance. And this is shown from the heatsink calculator results. So the main result is the thermal resistance of that heatsink, which will be directly updated in this input panel over here. And back in the case side cooling parameters, we can see a summary of the thermal resistance of the heatsink, of the heat spreader, and the thermal resistance overall from sink to ambient. One more thing, so very useful feature that we added to this calculator is that for a certain airflow to the heatsink, we get a certain resistance, but we know from manufacturers that it's very handy to get a heatsink performance chart. And this chart shows the different thermal resistances and how the heatsink performance changes with airflow. And this is a very helpful graph that helps with the design, and we also see how different design parameters affect the heatsink performance. So in this graph, we chose to show also the fin height as another design parameter, and this shows a plus and minus 20% change to the fin height and the effect on thermal resistance. All right, so now we have defined the device parameters. We have defined the PCB construction parameters, as well as the case side cooling parameters. And after defining all these parameters, we can move down and look at the results. And because we define two devices, we'll have two sets of results for device 1 and device 2. And the main reported parameter is the the temperature rise, as well as the junction temperature. So this shows the maximum temperature of the device and the delta T, or the temperature rise. And it also reminds us of how much losses are seen in the device. And in the next panel, we can go and look at a more detailed report. And if you remember, we had a circuit model for the whole system. And this is now for a half bridge. So we have two devices and two sets of resistances on each side. And there's also some thermal coupling between these devices. And if you'd like, you can look at each specific resistance separately for the board side or for the case side. For example, we can see R theta JC for the second device, the thermal resistance of the TIM, and thermal resistance junction to sink. We can also see the thermal resistance of the cooling solution and an overall thermal resistance junction to ambient through the case. And these resistances can then be simplified to just two junctions with the resistances to ambient and the mutual heating resistances, and then solved for the overall results that we have. So this is a detailed report for those that would like to have more information. The next panel is used to analyze how different loss estimates can affect the operating temperature, and we can also change the ambient temperature and the losses for the different devices. So let's say for device 1, we expect somewhere between 4.5 excuse me. So let's say we expect somewhere between 4.5 and 5.5. Then we get the range for the minimum junction temperature at this loss and the maximum junction temperature at the high estimate of loss. And this is done for device 2. So the minimum is assumed for both minimums, and the maximum is assumed for the highest expected losses. So for two devices, we can either define both losses for the two devices, or we can define an overall loss and a certain percentage distribution. So let's say the half bridge will dissipate between 6 and 9.5 watts, but we know that the distribution is almost 60-40, so we can choose that percentage and get similar values. And this is very helpful if we want to do some different loss estimates, and if we're not 100% certain of the estimates that we have. The final panel is also another feature that we've added to this calculator, and this helps us to track our changes, and if we'd like, it helps us also to save some of those results. So let's say we want to save this case, and we can call it, let's say, half bridge, and heatsink, say 400 LFM. We can name this case and add it to the list of cases that we have. And we can go back, let's say, increase this to up to 600 LFM and go back down and save the new set of results as half-bridge heatsink with 600 LFM. And when we save it, we see that we get another column with the name of the saved case and the difference in the output results. We can also decide to remove some of the heatsink parameters, change some of these design parameters, maybe use a lower conductivity TIM, thicker gap, and then going back and updating these results. You can also save those as well. And we can see that the temperature increased slightly. Actually, not slightly, by 10–15%. Okay, so this is the at the end of the thermal online tool, but I have to go back because we skipped over some of the stuff. And mainly if we go back and decide to use, let's say, a single device or the two devices as well, but you notice here that there's an option to parallel the devices. And this has been a quite requested feature. And what it does is it helps us to take this single device or the half-bridge layout, and we just minimize over here and parallel them and or array them in a certain layout. So we can take this device and then maybe place 3 in a certain row and maybe have 2 columns, or 2 columns and 3 rows in this case. And we can also increase the spacing between these devices by changing the array pitch and in X as well as in Y. And we can also decide to have it be off center in the X and in the Y direction. And you can notice that if we move slightly out of the heatsink, the app is has some intelligence, and it knows if we moved outside the borders, or maybe if we use a smaller spacing than we're supposed to. So this is supposed to be greater than 6 because 6 is the width of our device that we're using. And we can make sure that we have that. So let's increase our pitch slightly larger. So whenever we're ready and we're happy with the layout, we can go down and then calculate a new effective thermal resistance of the heatsink. And we will notice that the thermal resistance from the die to ambient will increase. And that's because we have more than one heat source on the heatsink. And we can also get the overall heatsink thermal resistance, and that's assuming the total heat, power going into the heatsink. And we can get the sink to ambient thermal resistance, and that's assuming a single device. And this value will be also populated in our case side cooling RSA value and will be used for the calculations. So also we can decide to show the parameter list, and this will show us the placement of the different devices, the coordinates, the size, width, length of each of the device, the heat dissipation in these devices, and the maximum case temperature, sink temperature at the base of the heatsink. And this paralleling feature can also be used for a single device, but it can also be used for two devices in a half-bridge configuration. And if we go back and define two differently sized FETs, we can see here that they appear also under the heatsink. So let's maybe use 3 half bridges, and we can also define the device orientation, so we can have them placed vertically or horizontally. And we can choose if we want to flip their placement, so to have the larger one on the left and the smaller one on the right, or vice versa. Same thing, whenever we're done, we can press calculate, and this will update the features of the heatsink and the thermal resistance from sink to ambient. All right, so this is regarding the heatsink calculator. So let's just recap. In the beginning, we have a bit of an intro and some user guide to help with navigating the online thermal calculator. We have the schematic and the figure, which updates depending on what parameters we select and what heating solution we select. So we can remove the heatsink and just have the PCB, and this will update the schematic and the thermal resistances. The device parameter is where we select the devices and define the losses. And if we have any vias in pad, we can choose to have different cooling solutions, and we can either only choose a PCB cooling, or we can also add a heatsink, which will add the heatsink panel. So the PCB parameters relate to the PCB stack up, construction, and thickness, and the airflow to the PCB, while the K-side cooling depends mainly on the TIM material, on any liquid or gel gap filler, and on a heat spreader if needed, and finally on the heatsink performance. And this heatsink performance can be calculated for a air-cooled rectangular fin heatsink by using the heatsink calculator. And also we can choose to parallel these devices if we have more than a single device over here by checking the parallel devices. And in the parallel device panel, we can set a certain number of devices, set the array pitch, and calculate the sink to ambient thermal resistance. We have simplified results, and these are also shown in the side panel for ease of access while we're scrolling in the online calculator. And 3 different features for the calculator is first of all, we can see a detailed result report with the individual thermal resistances that are modeled. We can also do a power loss analysis by varying the losses in the device and seeing how that affects the temperature. And also we can keep track of all our cases and do a certain comparison. So this wraps up the online calculator. And if you have more questions, or if you'd like more information on the topic of thermal management of GaN devices, you can refer to our How to GaN series videos. Or if you have any other questions, you can contact us using these links. And I hope you find this this calculator useful, and it will help you in your design process and in selecting devices. Thank you.